9.1, and by the end of today, you will be able to find resultant forces and tension. So find resultant forces and tension. Okay, and I said please draw a picture to accompany your work for each problem. Okay, so same thing with your homework when you're doing the story problems. Okay, so for example 1, a man is pushing a lawnmower with a force of 30 pounds exerted at an angle of 30 degrees to the ground. Okay, so the force is 30 pounds and it's at an angle of 30 degrees to the ground. And then what we have to do is find the horizontal and vertical components of the force. Okay, so we're going to start by drawing a picture. And your picture does not have to look exactly like mine for this. There is no direction. So I like to start with the ground. Okay, and I know that this person is going to be pushing down. So here's going to be my vector of force. Okay, and I like to draw my person. This is a short person, so probably a kid whose dad is making him mow the lawn. My dad never let me mow the lawn because he said I would ruin the lawn and cut my foot off. Okay, so here's our happy kid on a summer vacation mowing the lawn for his dad and mom. Okay, and then this is 30 degrees, an angle of 30 degrees. So if I'm going to find the horizontal force and the vertical force, I can use the same equation that we did for the past 2 days. So the magnitude is going to be the cosine of theta for the horizontal, and the magnitude is going to be this times the sine of theta is going to be your vertical. Okay, so in this case, the magnitude is going to be the 30 pounds. So we are going to do 30 times the cosine of 30 degrees and 30 times the sine of 30 degrees. Now, because this is an exact value on your unit circle, and we're not going to be adding anything together, you could find out exactly what it is. This is root 3 over 2. So when you multiply 30 times root 3 over 2, that would simplify to 15 root 3. And half times 30 is going to be 15. Okay, so then your final vector, again, you could write it as 15 root 3, 15. Okay, and again, that comes from 30 root 3 over 2. Okay, or you could write it as a decimal, which would be 25.98, 15. Okay, and then your horizontal is going to be your first component, and then your vertical is your second component. Okay, now our next example is going to be similar to some of the things we were doing yesterday. We're just going to extend that. So you have a river that's flowing south at 3 miles an hour. Then you have a swimmer who's attempting to cross the river, and he's going to head due east, and he swims at 2 miles an hour. Find the true velocity of the swimmer as a vector. Okay, so we are going to be finding the true velocity. Okay, so I do like to draw a picture, especially because this is something that you'd have in your textbook. Then you might want your own. And yesterday I talked about the relevance of the picture when you're trying to find that resultant vector. That's going to help you when you're trying to find the resultant vector. Okay, so we have the river that's flowing south. So I'm going to call this my R vector, and the magnitude to be 3. And then the swimmer is heading east at 2 miles an hour. So I'm going to make that one a little bit shorter. I'm going to call that one vector S. Now, all I have to find is the true velocity, but if I had to find the direction for this swimmer, I could figure out where his true direction is by making the parallelogram, right? So really, this swimmer is going to be headed in this direction. This is going to be the swimmer plus the river. Okay, and that makes sense. So picture this, okay? You're swimming east. This is you, this arrow, okay? You're swimming, doing fine. And then the river current comes in, and the river current is going south. If this is you and this is the river, what's going to happen to you? Yeah, you're going to get pushed, right? You're going to get pushed, and instead of here, now you're going this way. Yes. Okay, so that's why it makes sense that this would be the resultant vector. Because if you're swimming and the river's going down, you're going to end up going this way. Now that's one reason when I mentioned physics why you're going to do your head to tail method is so that you can get that. So if you were in physics, you would do the river is going down, your swimmer is going this way, and then you'd get your resultant force here. Okay, and if you want to do it like that, that's perfectly fine. Okay. All right, so what we have to find is the true velocity. If we're going to find the true velocity, which is the swimmer plus the river, first we have to find the vectors for the river and the swimmer. So for the river, we did this yesterday. This would be 3 cosine of. Now, what is your theta value going to be? So we can use this picture to help us, right? If this is the river, our theta value is going to be right here, which is going to be what? Close. Negative 90. See how we're going in the negative direction here? We're going clockwise. So your theta value is going to be negative 90. Or you could also write, instead of negative 90, you could write 270. Yep, so either one of those is fine. Okay, and at that point, your cosine is 0. Which means this is going to be 0. And your sine is negative 1. Which means you're going to have negative 3. Okay, so that's your river velocity. Okay, now we have to do the swimmer velocity, which this guy is going 2 miles an hour. And again, he's going east. So what's your theta value going to be? It's going to be 0. Okay, so this would be the cosine of 0 degrees to sine of 0 degrees. Okay, and at 0, we know the cosine is 1 and the sine is 0, which is going to give you 2, 0 for the swimmer. Okay, so then the true velocity is going to be the vector that is the swimmer plus the river. Okay, so if we add the horizontal components together, 0 plus 2, we'll get 2. Negative 3 plus 0, we'll get negative 3. And that is going to be our true velocity vector. Okay, now see how it's 2, negative 3? In what quadrant is my vector in here? 4. So does that make sense that my x is going to be positive and my y is going to be negative? Right? Those are things you should be thinking about before you turn in a quiz or a test. Okay? Does my vector make sense in terms of the position? Okay? Oh, question we've seen before. How is true velocity different from true speed? Well, remember that true velocity is the resultant vector. Now, this one didn't ask us for the true speed, but we could find out what it is, right? By taking what? By the magnitude. So the true speed is the magnitude of the resultant vector. Okay, so really if we wanted to find that, we could do 2 squared plus 3 squared, right? So 4 plus 9 would be 13. Square root of 13 is going to be about what? Has to be more than what, though? More than 3, less than 4, right? Somewhere between 3 and 4. Okay? All right. Now, the next question says, suppose that in example 2, the current is flowing at 1.2 miles an hour due south. In what direction should the swimmer head in order to arrive at a point due east of his starting point? When it says what direction, that's going to change where the swimmer is going. Okay? It's saying where should he head. Before he was going east, and then look, he got pushed down, and he's going southeast. Okay? So we have to figure out where does this guy have to swim in order to actually go east. Because if he swims east, he's going to get pushed down by the current. Okay? So if he wants to end up over here, he's going to have to adjust his course. Now, because it doesn't give us a new speed, we know that the swimmer is still going to be going at 2 miles an hour, because that was the same as in example 2. Okay, so in what direction? So that's what we're trying to find, is the direction, so we don't know if he's going east or not. All right, so we are going to create a picture for this before, well, let's do the north, south, east, and west. And then before we do that, I'm just going to talk to you about a few things. Before we put it on our beautiful, beautiful diagram. Okay, so remember before when we were drawing resultant vectors, like I gave you this was u and this was v, and then you had to find the u plus the v, which was the diagonal of the parallelogram. Remember that from the other day? Okay, so this is kind of similar to that, except now you are not going to be given the two vectors. You're going to be given the resultant vector and one vector. Okay, so we know that the river is going to be flowing south. This is what we're going to put on our graph. And we know where we want to go, and that is due east. This is going to be the river plus the swimmer. So if this is the diagonal of the parallelogram, I know that the swimmer is going to want to go somewhere in this direction. See how that's going to create the diagonal to the parallelogram? Can you see that? All right, let's think about it logically. All right, if the river's pushing me down and I want to go this way, I'm going to have to start swimming in this direction. Because if I'm swimming in this direction, okay, northeast, and the river pushes me down, it's going to push me down so that I go where? East. It's going to push me. If I'm going this way, okay, the river is going to push me down so that I end up going east. Okay, so that's what we're going to be putting on our diagram. So the river is 1.2. Okay, we don't know where the swimmer is going to go, so what I draw first is the resultant vector. And so to show that it's the resultant vector, I do that dashed. That might be a little too big, actually. Okay, and then the swimmer, because I know that this is going to be the diagonal, if you want to get an accurate representation, zoom in so you can see this. If you want to get an accurate representation of where it's going to go, just think of it like this. It's like you're connecting these 2 points, but you're just going to do that at the origin. So now I'm just going to move it up here. Okay, see how those are parallel, and that's going to create the parallelogram? Okay, and I don't have to have that there. Okay, I just have my swimmer. Who is going 2 miles an hour. Okay, so now when you're trying to find the direction, you're trying to find theta. This is going to be my theta. Okay, so then let's go ahead and create a vector for the swimmer. So the swimmer is going 2 miles an hour. We don't know the direction, so we're going to call it cosine of theta and sine of theta. And that's all I can do at this point. Now we're going to do the river vector, which is 1.2 cosine of, what's this angle? What's the angle? It's still negative 90 degrees, right? Or 270? Okay, so at negative 90, the cosine is what? 0. So then this is going to be 0. And then the sine is negative 1. So negative 1 times 1.2 will be negative 1.2. Okay, and again, that should make sense. See how the arrow's going down? So you should have 0 and then a negative value, okay, which is going to be the magnitude. Hey, now if I want to find out what direction he should head, what I can do is use the resultant vector. Okay, so the resultant vector, S plus R, is going to be 2 cosine of theta, because 2 cosine of theta plus 0 is just 2 cosine of theta. And then when I add 2 sine of theta to negative 1.2, it'll be 2 sine of theta just minus 1.2. Okay, now here's where we have to use some logic. Okay, so you're swimming along, going east. This is you, this arrow. Okay, and I want you to tell me what could knock you off course. Okay, think in terms of the current. Okay, what type of current would throw you off from going east? Coming from where? Okay, so if it's coming from the north, isn't that going to push you down and then you're going to start swimming this way? I'll use this. Okay, so you're here, right? Oh no, it's coming from the north. I'm going this way. Okay, what other type? South. Oh no, I'm going this way. Okay, so if it's coming from the south or north, you're not going to be going east or west. If the current is coming towards the east, what is that going to do for you? It's going to make you faster, right? Okay, and it's going to help you. If it's coming from the west, it's going to make you go slower, but is it going to push you off course? No. Okay, so you're going to have to fight against it, okay? But you're still going to be going east or west. Okay, now, we have to use that to help us solve this. So, in order to head east, we want the vertical component to be 0. Okay? If it wasn't, it would push us north or south. If it wasn't, it would push the swimmer north or south. Okay, so we want the vertical component to be 0. So what I can do is set the vertical component equal to 0, and then I can solve for theta. So if my vertical component is 2 sine of theta minus 1.2 equals 0, I'm going to solve this for theta. Okay, is it okay if I do a couple steps in one? Because your first step would be to add the 1.2 over, right? And then your second step would be to do what? Divide by 2. So is it okay if I just put sine of theta equals 1.2 divided by 2? Okay, so you're adding and then dividing the 2. So then to find theta, you're going to do the inverse sine of 1.2 over 2. Again, make sure you're in degree mode. And you should get 36.7 degrees. So then you're going to go ahead and put that with a direction. So in your picture, this is nice because you can see what direction you're heading. What direction is this? Direction is this here? North of east, yep. Okay, so it's 36.87 degrees north of east. Okay, that's where he should head. You could also say east, 36.87 degrees north. You could say north, 53.13 degrees east. Those would be correct as well. Okay, so those are other options. All right, let's go to the next page. Okay, so on the back it says that you have to describe your forces. So the first thing we're going to do is describe the force. Define the force. Right, so for number 1, the force is the push or pull on an object. The resultant force is the vector sum, which is exactly what we were doing with our resultant forces in our drawings, is the vector sum of forces acting on an object. And the last one you've probably heard before is equilibrium. Do you guys know what equilibrium is? What is it? Don't do that. What's equilibrium? Okay, yeah, it's where two things balance out. So it's a state in which opposing forces are balanced. All right, so we're going to use those in our next example. So the forces F1, F sub 2, all the way up to F sub n that are acting at the same point P are said to be in equilibrium if the resultant force is 0. So that means if the sum of those forces, F sub 1 plus F sub 2 plus all of them up to F sub n, if the sum of those forces is going to be 0. What we have to do is find the resultant force, the resultant forces acting at P, and then B, the additional force required, if there's any, for the forces to be in equilibrium. Now the first one is pretty nice because they just give you the vectors. There isn't any work to find them. So when you're trying to do part A, when you're finding the resultant forces, all you have to do is find the sum of those forces. So F sub 1 plus F sub 2 plus F sub 3. Okay, so if you're adding those together, F sub 1, the horizontal is 1, and then plus 1 for F sub 2, and then plus negative 2 for F sub 3. And then for the vertical, I have negative 1 plus 1 plus 1. Okay, so I'm just going to add those up and then simplify. Okay, so 1 plus 1 is 2. 2 minus 2 is going to be 0. Negative 1 plus 1 is 0. 0 plus 1 is 2. Or sorry. Thanks. Okay, so negative 1 plus 1 is 0. 0 plus 1 is 1. Okay, so you're going to have 0, negative 1. For B, you have to find the additional force needed for them to be equilibrium. So we have how many forces in part A? 3. So we need a fourth one to balance this because it's not 0, 0. So basically what you want to do is the opposite because that's what's going to add to make 0. Okay, so the opposite of 0 would just be 0. Okay, and then the opposite of 1 would be negative 1. So if you added those two vectors together, you would get 0, 0, which would be equilibrium. Okay, so we're going to write a little note about that. So the additional force will be opposite of the resultant force to produce equilibrium. If the resultant force is 0, 0, and sometimes it will be, then no additional force is needed. Bless you. Okay, now for number 2, we actually have to calculate what the vectors are going to be. And you should have had forces on here, but they are not, so we're just going to add them real quick now. So this should be labeled as 5, and this one should be labeled as 3. Okay, so like I said, this one was nice because they gave you all the forces. Now we are going to calculate the forces. So to find F sub 1, we can use what we know about horizontal and vertical components. How would I find what my horizontal component is of this? Just do what? How do you find it? How do you find the horizontal component? The cosine of theta times your magnitude. Okay, so what's theta going to be for this? 45, because you start here, and then you're going to go to your line. So your theta is 45. Okay, so force 1 is 5 times the cosine of 45 degrees, and 5 times the sine of 45 degrees. Okay, now you could write this as an exact value, 5 root 2 over 2 and 5 root 2 over 2. We are going to be adding them together though, so we can just write them as a decimal, which is 3.54, 3.54. Okay, remember that that makes sense that those are the same because that the cosine of 45 and the sine of 45 are going to be the same. Now we're going to do F sub 2. So the magnitude of F sub 2 is going to be 3. What do we think the cosine is going to be? 195. Okay, so you have to start at 0, right? And go all the way here. Okay, so then to find your theta for F sub 2, your theta is going to be 180 plus 15 degrees, which will give you 195. You could also go the opposite way. Okay, that would be fine too. Okay, this we are going to need to calculate since it is not a place on our unit circle. Okay, so 3 times the cosine of 195, you should get negative 2.90, and then negative 0.78. Now let's make sure that these make sense according to their positions. So your first force is in quadrant 1, right? Quadrant 1. Okay, and then so this is positive and positive. Okay, and then this one's negative, negative. Does that make sense for its position? Yeah, because it's in quadrant 3, and in quadrant 3 you have negative x and negative y. So these are things you should be checking when you do like a test or a quiz. When you write that down, does that make sense with what the problem's asking you? Okay. All right, so now we're going to find, for part A, the sum of the forces, F sub 1 plus F sub 2. So when you add 3.14 to negative 2.90, you get 0.64. 3.54 minus 0.78 is going to be 2.76. Okay, and that will be your solution for A. For B, do we need an additional force? Yes. Okay, if we didn't, we would just write no additional force needed. Okay, but we do. So what are we going to call this additional force? F sub 3. Okay, and then Colin, what's F sub 3 going to be? Good. Okay, so you always want to do the opposite. Okay, now I do want to just give you a heads up that on your homework, you're going to have some that are on a grid. Okay, so you don't have to draw this. 2, 3, 4. Just going to put these here. Okay, so if this is what you had, okay, and they only tell you that this is F1, this is F2, this is F3, this is the point P, do we know what the names are going to be of these vectors? Can we find that out? Can we find out their horizontal components and their vertical components? Yeah, because we can just count, right? Can't you find what the horizontal and vertical components are by counting the spaces? So if this is 1, 2 spaces away, and this is just 1 space up, then this vector would be 2, 1. Right? See how this one isn't going anywhere left or right? So then what would your vector start with? 0. And then let's count how many units it's going down. It's going down 1, 2, 3. So then it would be 0, negative 3. Okay? From this point here, okay, I'm going to the left 1. So this would be negative 1. And then I'm going up 1, 2. So it would be negative 1, 2. Okay? You guys remember that from a couple days ago? We actually drew them in the plane. That's going to be the same type of thing. Okay. All right. And then the last thing we're going to do today is tension. So if you are in physics, the way that we're doing this is a little bit different, but that's okay. If you guys want to use the other method on your homework, you can feel free to do that. Okay, so you guys are so sweet, and you want to show me your love and appreciation, and you decide to hang a 50-pound heart from a string in front of the school as shown below. So let's label this as 50 pounds. 50 pounds of love and appreciation. Thank you, guys. Be nice to the person that grades your test, JC. Okay, and then it's in front of the school as shown in the figure below. So you're going to find the tensions T sub 1 and T sub 2 in the string. Now notice that T sub 1 and T sub 2 are vectors. So when you find those tensions, you are going to be writing your solution as a vector. Okay? So one of the first things we have to know about tension is that the up forces are going to equal the down forces. Okay? Think about what would happen if it didn't. Okay? If it didn't equal, okay, if what was holding this up did not equal the weight going down, what would happen to this weight? It will fall, okay? Or else the weight would fall. Okay, now the other thing we have to know is that the horizontal components are equal. And let's think about what would happen if they weren't. Okay? So let's say me and Logan are in a tug of war. And, well, Logan's obviously going to win. He's stronger than I am, right? So if we're pulling the string, what's going to happen to me? And I'm going to go in what direction? I'm going to go forward, right? So if T sub 1 was pulling more than T sub 2, this weight would start moving, okay, in that direction. Okay? And obviously we don't see that. So if not, there would be motion. Okay, so think tug of war. Okay, if the tensions aren't equal, then people are going to move. Or sometimes tug of war goes on a long time because the tensions are equal and they don't. Okay, so we are going to be using the horizontal and the vertical components. We're also going to be using a system of equations and substitution. But first, we are going to use alternate interior angles. So if we're looking at this picture, what I can do is think of it like this. Okay, so I'm just going to draw a nice dashed line here. Okay, and I'm going to set up two triangles. Okay, now using alternate interior angles, if this is 58 degrees, I know this is going to be 58 degrees. And if this is 35 degrees, then this is going to be 35 degrees. Okay, now I like to set up the triangles separately. You don't necessarily have to, but I like to do it to show you guys where that's coming from. Okay, so this is going to be my tension 1, my T sub 1. Okay, and my T sub 1 triangle, this angle is going to be 58 degrees. Now remember, with a vector, this is going to be your horizontal component, this is going to be your vertical component. So your horizontal component is the magnitude, which is T sub 1 times the cosine of 58 degrees. And your vertical component is going to be T sub 1 times the sine of 58 degrees. Now I can set up something similar with my second tension. Okay, with T sub 2. And sometimes I'll make these dashed. Okay, so then this is going to be, this is 35 degrees, T sub 2 times the cosine of 35 degrees. And this is going to be T sub 2 times the sine of 35 degrees. Okay, now that we have that, I'm going to give you a series of steps that you can follow to help you solve this. Okay, so your first step is going to use the fact that horizontal forces are equal. We are going to set up that equation and we are going to solve it for T sub 1. Now really, if you wanted to solve it for T sub 2, you could. I just like to solve for T sub 1. Okay, so my horizontal force for T sub 1 is T sub 1 cosine of 58 degrees, and that has to equal the horizontal force in T sub 2, which is T sub 2 cosine of 35 degrees. Now we're not going to do any rounding to the end. So when I'm solving for T sub 1, I'm going to divide both sides by what? Cosine of 58. Okay, so T sub 1 is going to equal t sub 2 times the cosine of 35 degrees divided by the cosine of 58 degrees. You can also write this t sub 2 to the side. That would be fine too. Right? Now what we're going to do is take into account that the up forces have to equal the down forces. Now, what is the down force in this picture? What's pulling down on the string? The weight, okay? So the down force is going to be the 50 pounds. The up forces are going to be the sum of the vertical components. The down force is going to be the weight of the object. Okay, so when I set this up, I'm going to have the up forces, which are t sub 1 sine of 58 degrees, plus t sub 2 sine of 35 degrees, equal to the weight, which is 50 pounds. Okay, now if you're in physics and you're thinking about if you have to do any type of conversion, you don't, and that's because it's already in pounds. Okay, so usually when you do things in physics, you have a mass, it's a kilogram, and then you do a conversion. Because it's in pounds, you don't have to worry about that. Okay, so what we're going to do is we are going to substitute for t sub 1. So we know that t sub 1 is equal to this. Okay, which means we can plug in t sub 2 times the cosine of 35 degrees divided by the cosine of 58 degrees. Now that's times the sine of 58 degrees. Don't forget to multiply. I've done it before. It's not fun. Don't get the correct answer. Okay, but that is something small that you could miss. Okay, and then what we're going to do is we're going to do the calculations in our calculator, and we're going to keep them that way until the very end. Okay, so when I do this, when I do the cosine of 35 divided by the cosine of 58 and multiply that by the sine of 58, I might write on my paper the 1.310, and then I'll write dot, dot, dot that shows I'm keeping that. Okay, and then I would add that to the sine of 35 degrees. If you have an older calculator like mine, you can't just click on it. So this is going to be 1.884 dot, 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 t sub 2. So you're just adding your like terms here. When you do the sine of 35, you get 0.57. 3 dot, 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 t sub 2 equals 50. Okay, so all you're doing here is solving for t sub 2. The only difficult part is you have decimals. So when you're solving, you're going to divide by that value. So you're going to divide by 1.884, and that's going to be your tension for t sub 2. Okay, that's going to be the magnitude of your string. So this you can go ahead and round to the nearest hundredth, which would be 26.54. Okay, and then you are going to substitute that into the equation in step 1. Okay, and then that will give you your t sub 1. So T sub 2 is 26.54 times the cosine of 35 degrees divided by the cosine of 58 degrees. Okay, so I'm going to take that exact value and multiply by the cosine of 35, and then I'm going to divide it by the cosine of 58. And then I get 41.02. Now remember, I said that your solution is going to be a vector. Okay, so we will finish that one on Monday. Your homework is online. There are two tension problems, 73 and 74. If you want to start them, go ahead. But when we finish this up on Monday, you could do those two problems on Monday.